So in this question, we've got differentiation meets parametric equation, so parametric differentiation. So to find the equation of a line, in this case the line is the normal to the curve, we need to find a point on the line and the gradient of the line. Well, we've got the x coordinate of the point on the line, but we need to find the y coordinate. So when x equals 2, we know that 2 is going to be equal to 1 over t minus 1 because that's the definition of x. Rearranging that gives a value of t of 3 over 2, and then when we put that value of t into the expression for y, we get the value of y. So we've now got out the coordinates of our point on the line. We now need to know the gradient of the normal. Well, let's find the gradient of the tangent first. And we use dy dx, which is the gradient of the tangent, equals dy dt divided by dx dt. This is the parametric differentiation. Differentiating y to give dy dt gives 6t plus 2, and this is t minus 1 to the power minus 1, so when we differentiate that, we get minus 1 t minus 1 to the minus 2. So dy dt divided by dx dt gives us 6t plus 2 divided by minus t minus 1 to the minus 2. So to find the gradient of the tangent, we put this value of t into that expression, and we get the figure for dy dx of minus 11 over 4. But remember, that's the tangent, the gradient of the tangent, and we're trying to find the gradient of the normal. So we want the negative reciprocal of that. So that's 4 over 11. Then we can use the equation y minus y1 equals mx minus x1, and y minus 39 over 4 is the y1 equals mx minus x1 x is 2. We can tidy that up a little bit to have only integers. Actually, that's not quite true. This isn't an integer, but integer coefficients of x and y. If you wanted integers, you could multiply by 4, of course. Okay, so we found the equation of the normal to the curve when x equals 2. Now we've got to try to find where the normal meets the curve. So there's the equation of the normal that we've just found. And we find where that meets the curve. Well, the curve is defined with these parametric equations here. So we can put this expression for y there, and this expression for x there. So that's what we get. This is the equation that arises from finding and effectively solving the normal and the curve simultaneously. What I've decided to do here to make sense of this is to multiply through by t minus 1 and then simplify, and I get the cubic in t. Popping that into my calculator, I get 3 values of t. I'm not surprised by t equals 3 over 2 because that's the value of t we get when x equals 2. We know that that is one place where the normal cuts the curve, so that's nothing new. But then we've got these 2 other values of t. Substituting those 2 values of t into the values for x and y gives us these 3 values for y and those other 2 values for x, other than the 2 that we already know. So there we are, those are the coordinates. I've expressed them to 2 decimal places. It's probable, there may be possible to express them in surd form if you had solved the cubic equation via an analytical approach rather than using a calculator. Okay, so there we are.